So let's get this shindig going. Here we go. Getting everybody. Let's do this and that. Here we go. And I will also get the link here for the chat. Alrighty, so here's the link to the Pear Deck for today's activity. You can also go to joinpd.com and use the join code on the screen that's being shared right now. VEWUAW. All right. And this is what we're going to do today to get some practice on section 8.3. All right, so here we go. We're in estimating a population mean. That is section 8.3 in chapter 8 about estimating with confidence. All right, our first slide here is just review. This is a why is this causing me problems today? Can you guys see this whole slide? My Pear Deck is saying that it's not showing the whole slide.
I can still see it.
You can? Okay. I don't know why it's sending me an error right now. All right. So this slide is just a review of some of the key concepts that we need from section 8.3. Like if we're just going to boil it down, these are the things we need to take away. All right. We have conditions for constructing a confidence interval about a mean. Right. And that is it needs to be random. We need random. Right. It has to come from a SRS or a randomized experiment. We have to have the 10% condition satisfied when sampling without replacement, which typically is the kind of sampling we end up doing. And we need to check the normal/large sample condition. Right? If the parent population is normal, so will the sampling distribution. If we don't know what shape this parent population is, but the sample is large enough, then we get to use t distributions and everything works out. If neither of those things are satisfied, we have to graph our distribution from our sample, look at the shape, decide whether or not it is relatively normal, right? As long as it's not getting any outliers and it's not terribly skewed, we're good to go. We have our one sample t interval for a population mean. This is our inference method that we learned in this section. It's very similar to the inference method that we learned for 8.2 about population proportions. It gives us the interval, right? When the conditions are met, a C% confidence interval for the unknown mean mu is x bar plus or minus t star times s sub x divided by the square root of n, where t star is the critical value for the t n minus 1 distribution, which is that degree of freedom that we look up on table B, with C% of the area between negative t star and t star. We have choosing a sample size for a desired margin of error when estimating mu. Again, this is a very similar process to what we did with proportions, right? To choose a sample size, we need to have a reasonable value for the population standard deviation from an earlier study, right? Or from a pilot study, test study, something. We need to have something to use for the standard deviation. We need to be able to find a critical value z star from a standard normal curve, right? And again, estimating the sample size uses z star, same as we use z star in proportions. So we're going back to table A. Right? Solve the inequality for the margin of error, and z star times sigma divided by square root of n less than or equal to margin of error. We solve for n. Lastly, when we're doing problems about confidence intervals, when we're constructing and interpreting a confidence interval, when you see those words, construct and interpret, blah, 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 confidence interval, we're using this 4-step process, whether we're dealing with proportions or means. We need to state what parameter do you want to estimate and what confidence interval, plan, identify the appropriate inference method. Right? We have one sample t interval for a mean, one sample Z interval for proportion. Check conditions. Do, if the conditions are met, perform calculations, right? Find your interval, and conclude, interpret your interval in the context of the problem. And that's the sentence, the whole phrase of we are, 95% confident that the interval from this to this captures the true mean, blah, 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 based on our context. Right, so these are the key takeaways. If you don't have anything else in your notes about section 8.3, you should at least have these things in some way, shape, or form. Right? Is there any questions about these things before we get started? All right. Does anyone need a moment to write any of this down for their notes? Okay. So we're going to start with multiple choice, kind of like we did last week here. So you should have a set of choices here. Why are we using t? Here's the name of this question. One reason for using a t distribution instead of the standard normal curve to find critical values when calculating a level C confidence interval for a population mean is that, and please make the selection that completes this sentence. There's only one correct answer out of the 5 options. All right. So let's talk about this one here. We have one reason for using a t distribution instead of the standard normal curve to find critical values when calculating a level C confidence interval for a population mean is that. Most of you guys who answered this question got this correct. B. It was option B. Z requires that you know the population standard deviation. All right. And we do not, because we don't know the mean. Is there any questions, anything I can clarify for you on this first multiple choice question? Go to the next one. All right, you have an SRS of 23 observations from a large population. The distribution of sample values is roughly symmetric with no outliers. What critical value would you use to obtain a 98% confidence interval for the mean of the population? I believe this link will work. I'll put it in the chat as well if you need a copy of table B to use. Hopefully that works. You will need to do some scratch work for this one, but it is a multiple choice. I suggest doing the math though, so you might want to have a little piece of paper, sticky note, something. And use table B, find that critical value. Alrighty. So on this one here, the correct answer was E, 2.508. All right, and let's look at where we get that from. All right, so if we're looking for this problem here, we have a critical value. We had an n equals 23. That was our sample size. So that means our degrees of freedom that we then find on table B is 22, one less than the sample size. All right, so then we go to 22 on table B, and we're at a 98% confidence. Right? The intersection of those two, the row and column, is 2.508. Right? That is our critical value. Right? Any questions? Anything I can clarify for that one? Alrighty. Oh, this is not a negative sign. Sorry, that's just a dash in between the letter E and the value. Our critical values are always going to be positive, whether we're using table B or table A. No, it's okay. Yeah. We're dealing with so many symbols and stuff. It's good to get clarification. I probably shouldn't have used a dash. So I apologize for that. It was probably a poor choice in design. All right. Anything else I can clarify? All right. Next multiple choice, we have quality control. A quality control inspector will measure the salt content in milligrams in a random sample of bags of potato chips from an hour of production. Which of the following would result in the smallest margin of error in estimating the mean salt content mu? Quality control. Ah, that's annoying. I'm sorry, Daniela. I don't know why it's doing that either. That's frustrating. All right. So in this case, right, the option B, 90% confidence with n equaling 50 is going to result in the smallest margin of error in estimating the mean salt content mu. And the best kind of way I can show this is by looking at table B and the difference in how things are calculated. So we're going to look at that real quick. So when calculating a margin of error, we use everything to the right of the plus or minus sign for our calculating our interval, and that's the t star times s sub x divided by the square root of n. A smaller critical value creates a smaller margin of error, right? And multiplying by a smaller number creates smaller numbers. And dividing by larger numbers creates smaller fractions, right? So multiplying two smaller numbers together gets a smaller result. And so between those two ideas, if we look at table B, right, when n is 25, we have a degree of freedom of 24. When n is 50, we use 40. We have 49 as a degree of freedom, but we use 40 on the table. With 100, we use 80. Because again, we can't go over. We have degrees of freedom of 99. We have to go back down to 80. And we can see that between the four actual numbers we can use with a sample size and degree of freedom, 1.684 is the smallest critical value we can get, and when n is 50, that also creates a smaller fraction. The only reasoning I can come up with as to why using a sample size of 100 for any degree of freedom isn't favorable is because to get the smaller numbers, we have to have a larger or a less confidence, and that's not really what we want. And so because it's not restricted to a certain confidence level, we can't choose that option because the range of possibilities is too big. Okay, is there anything I can clarify about this problem? All right, next one. And this next one is not multiple choice. Leave. So this one you're gonna need to have some scratch paper to do. We have Willows in Yellowstone. Writers in some fields summarize data by giving X bar and its standard error rather than X bar and S sub X, or the sample standard deviation. Biologists studying willow plants in Yellowstone reported their results in a table with columns labeled X bar plus or minus SE, or standard error. The table entry for the heights of willow plants in centimeters in one region of the park was 61.55 plus or minus 19.03. The researchers measured a total of 23 plants. We need to find the sample standard deviation for the measurements, which means we're going to have to use that formula SE equals S sub X divided by square root of N, set it up with the known information, and solve for S sub X. All right. And then just whatever solution you find, you'll type it in the entry here. Alrighty, everybody. We're going to talk about this one. I saw a few people who successfully got the result here. I'm going to allow you guys to keep access to this screen. I'm not going to progress the slide here, but I'm going to switch over to my OneNote to show you guys the work that goes with this one. So here we go here. So we're provided that we have the entry of 61.55 plus or minus 19.03. We're told that this is using the format that the first number is X bar, the second value is the standard error. All right, and so we use this information. We know that the formula for standard error is S sub X divided by the square root of N. The standard error is 19.03. N is 23. We don't know S sub X. So we set up our equation here, 19.03 equals S sub X divided by square root of 23. I multiply each side by the square root of 23. That cancels the square root of 23 on the right-hand side, brings it over to the left. Square root of 23 times 19.03 equals 91.265. And that is the value of S sub X, and this is in centimeters. That was the unit from our context. Okay. So there we go. Is there any questions or anything I can clarify? All right. So it looks like I'm looking through you guys' responses here, and some people are saying they're confused. Some people are saying my page contains an error. I'm not sure why Pear Deck is not cooperating today. Man, I have to figure this out. If you are confused, would you mind telling me what's causing your confusion, or something I can clarify, or something you'd like to see that might help? All right. Well, so again, here's the solution, 91.26 centimeters. It doesn't like my math notation in here. I think that's the issue. Pear Deck's not happy with my math. We'll do it differently. All right, here's our last question for the Pear Deck here. There's a lot of context here. All right, so a bunion on the big toe is fairly uncommon in youth and often requires surgery. Doctors use x-rays to measure the angle in degrees of deformity on the big toe in a random sample of 37 patients under the age of 21 who came to a medical center for surgery to correct a bunion. The angle is a measure of the seriousness of the deformity. For these 37 patients, the mean angle of deformity was 24.76 degrees. The standard deviation was 6.34 degrees. A dot plot of the data revealed no outliers or strong skewness, which means we're okay to use our t-distribution. We want to construct and interpret a 90% confidence interval for the mean angle of deformity in the population of all such patients. Alrighty, we'll talk about this one in just a moment. I see some people still putting in some solutions here. Remember, we're finding an interval of values, so you should have a lower value and an upper value that create your interval. It is common to list the smaller value first in an interval. Right, so you have the lower one first, upper one second. And that creates your range of plausible values. Okay. So you can see some people are still typing in there. I'm not going to progress to our next screen. I'm going to look at the work. Right, so if you were maybe confused as to where to go and how to start this, we're going to go through that whole our 4-step process here to show how we get there. Right, so if you want to go to the shared screen, we're going to look at the work here. All right, so here is our problem. And notice I've outlined the 4-step process here to kind of show how it gives us that kind of like roadmap on answering these questions. So we're going to start by stating we want to find mu equaling the true mean angle of deformity with a 90% confidence level. So we've stated my parameter, mu, what it represents, and the confidence level that I'm going for. Next, we plan. If conditions are met, we will use a 1 sample t interval for mu. That's our inference method. Again, I wasn't expecting you guys to type all of this in your responses. I'm being much more explicit in the work that I'm showing here. All right, so if conditions are met, that's part of planning. I got to check my conditions. Random, the patients were a random sample, so we're good there. 10%, we're going to assume that 37 is less than 10% of all such patients. They didn't tell us how many of these types of patients we have in the population. But because they gave it to us as a problem to solve, it's safe to assume that 10% condition is met, right? The only time sometimes the 10% condition will not be satisfied, they're going to tell you what size the population is, so you can actually do that calculation and be like, oh, hey, that's not 10%, or that's more than 10%, right? Large sample, right? We don't know what the parent population is. We were told that this distribution was not skewed and didn't have outliers, but it also satisfies our large sample condition because 37 is greater than 30, so we can use the t-distribution. So we move on to the do step, and again, I'm listing out the data I have. X bar is 24.76, S sub x is 6.34. The 90% confidence with a degree of freedom equaling 36, which means we use the degree of freedom 30 from table B, gives us a t star of 1.697, and n is 37. So that gives us this interval to find, right? X bar plus or minus t star times s sub x divided by the square root of n, 24.76 plus or minus 1.697 times 6.34 divided by the square root of 37, and we get, when subtracting, we get 22.991, or if you want to round to 22.99, that's totally fine. And an upper bound of 26.529, or if you're rounding, 26.53 as the upper bound. All right, so this left-hand bound is from subtracting, right, the margin of error. Right-hand side is adding the margin of error. And so then we can make our conclusion, right? We are 90% confident that the interval from 22.991 to 26.529 captures the true mean angle of deformity in the population of all such patients. Right? If you're stopping at, we are 90% confident that the interval from 22.99 to 26.529 captures the true mean, and you stop, you're not going to get full credit for that response because you didn't relate it back to the context. You must finish up with the actual context, the true mean angle of deformity in the population of all such patients. Now it ties back to our original context. Is there anything I can clarify on this example or anything else that you'd like to see? Okay. Alrighty. So then, that's the end of our Pear Deck. So we're going to stop this. Stop sharing my screen. All right, so with that, this is essentially the end of chapter 8. Right, this was section 8.3. We did 8.2 last week, 8.1 the week before. So we're now moving into assessment time for chapter 8. Right. All of the practice problems with their solutions in our class resources are available. Right. Right. So if we're in the class here, I highly recommend you guys use some of these resources. There's a lot of good stuff in here. All right. If we go into our modules, we got a lot of stuff ready here for you. Minimize chapter 6 and 7. Right. We've got practice problems and solutions for 8.1, practice problems and solutions for 8.2. Those are all ready to go. Right. They're also a great little review spots, right? With our practice problems, I have formulas and things that you need, similar to what I had at the beginning of our Pear Deck slide here, that help you review for those sections. Right. But all of our practice problems and solutions are available. I recommend doing those, especially with content if you're not comfortable with some of these things yet. We have our Desmos activity from last week. I will link this activity from this week. This is set up as an assignment for those people who did not participate during class or were absent. Right? They need to be able to get credit for doing these things. The multiple choice assessment is posted and available. The free response questions will get posted later today. I finished writing those and finding solutions for them yesterday because I decided to just make my own this time, and that takes a little bit of time to make sure I have problems that actually work. So those will be posted and made available later today, and all of Chapter 8 will be online. All right, and we'll be beginning Chapter 9 next week. Okay. Is there any questions, comments, concerns, or anything else I can support you guys with before we go? All right, if anything does come up or if you have some questions and you'd like to stick around and ask, please feel free to do so or send me a message later. Other than that, I will see you next week. Have a great rest of your week and an awesome weekend.